What's up, guys? So far, we've talked about standard deviation, kind of what that means, where z-score is a location, how many standard deviations away from the mean, above or below, and sometimes we're not at exactly 1, 2, or 3 standard deviations. And then today we're going to look at like that shaded area, like what percent of that shaded area that we've been looking at are we actually shading. So we're going to start off with recalling the heights of WNBA players and NBA players, and then going through and visualizing the results. So using the mean and the standard deviation of each one of those, we get something like this. So with the WNBA player, we have a mean of 72 with a standard deviation of 2. If I start with my mean in the middle and go up 2 and down 2 3 different times, I get a graph that looks like this. And I'm asked, I believe, on here something about maybe 80 inches, which is why I have that labeled. I'm going to go back and look. No, I don't. Maybe I'm just out of order. So maybe this is my next slide. I apologize. So I think what I'm looking at is the next slide talks about which one of these is more unusual, a WNBA player with 80 inches or an NBA player that is 87 inches tall. And so we should be able to look at these and kind of see where they're placed with the comparison, the mean and the standard deviation on each one of those. And if so, I can view that, and then I can also look at the z-score, which kind of tells me like how many standard deviations away from the mean each one of those would be. And we talked about z-scores. It's the data value minus the mean over the standard deviation. So our WNBA and our NBA, we would do these calculations, and I would get a z equals 4, which means 4 standard deviations above the mean, and 2.67 would be 2.67 standard deviations above the mean. So that line would be in between 2 and 3. So which one of these would be considered more unusual? And a z-score of 4 means 4 standard deviations above the mean, which is way more unusual, and we would say to be closer to the mean, we would call more typical or more normal, because that's where we would think of the average to be. So here we're just kind of comparing these two z-scores. We can also see that from the graphs that we created a second ago. Which one of those is normal? Well, 80 inches in the WNBA player is like way taller than, there may be one player that's 80 inches tall, the tallest person in the WNBA. With the NBA, it looks like they're still tall, 87 inches, but it's not as abnormal as having somebody that's 80 inches in the WNBA. Okay. So this is kind of like a multiple part type of problem that we're going to do. Now we're going to talk about how to find the proportion of a given value on a normal distribution, and we're going to use our calculator to do this. So this is what area are we shading, and what does that area represent in terms of the entire graph that we have. So we're going to start by hitting the second vars in our calculator and selecting the option 2 for normal CDF. And these are our possible options that we can have. If we're going to start by shading, and if we're shading the left area, understand that while, yes, we do talk about 1, 2, and 3 standard deviations, if I were to like just kind of roughly sketch like 1, 2, 3, like we have this tail end that goes on forever, like on both of these sides. So we're not just talking about 1, 2, and 3. We can go beyond 3, as we saw with the height of 80 inches in the WNBA. It's just the likelihood of being out there is not very high. So when we have the left shaded area or the right shaded area greater than or in between, we're going to type these in for our into our calculator. And if we're left shaded, we're going to use the negative 9999, basically to indicate that goes on to negative infinity. And the highest value that we see will be the data value that we're given precisely like at this location right here. When we're looking at finding the shaded area in between two numbers, you just take the smaller number for the lower and the largest number for the upper. The little U looking symbol means mu, so you guys know what mewing is. And then that sigma. You also know what sigma is for standard deviation. We're looking for those symbols to plug in, and then if we have something greater than, then the lowest value is going to be the data value we're given, and then that goes to positive infinity, or we would write 99999. So let's look at an example real quick. Approximately what percent of NBA players are shorter than 69 inches? So we already have our WNBA player normal distribution already made. What I want to start with is labeling on this graph where is 69 inches, and then shading this area with respect to what the problem is saying. So I'm saying what proportion of WNBA players are shorter than 69 inches. So there's 69 inches. This little shaded area represents the proportion of WNBA players that would be shorter than that. So how do I go and I figure this out? We're not going to do the empirical rule. We're gonna actually plug this into our calculator. So we're going to type in our lower, which since we're unbounded on the left, our lower one's going to be negative 99999, and then our highest upper bounds is going to be 69. We're given that we can see our mean in the middle at 72, and we're going up and down by 2, so standard deviation's 2. When I type that all into my calculator, I get a proportion of about 0.0668, and we should be able to look at this graph and kind of compare, like, out of the whole, right? If you have the whole thing as being 1, we have about 0.0668 of this graph shaded, and it should kind of represent that. I mean, we should be able to see that's not a whole lot of the graph that's being shaded. We can also write this as a percentage. In this problem, I'm asking you to write it as a percent. And in Delta Math, you need to make sure you pay attention to how I'm asking, or how Delta Math is asking. So as a percentage, we can just move that decimal place 2 units over to the right, or multiply that proportion that we get from using this normal CDF by 100, and it will give us 6.68%. So I should look at my graph and say that about 6.68% of this graph is shaded, which represents NBA players or WNBA players that are shorter than 69 inches. What if we were to look at approximately what percent of WNBA players that are taller than 76 inches? Let's figure out where that goes on our graph. There's 76 inches, which is 2 standard deviations above the mean. And the shaded area that I want are ones that are taller than that. So this little area right here. And it doesn't stop at 78. It just looks like that. It continues to go on and on. And obviously we can go all the way to 100 inches, but that's probably, I don't think there's anybody, there's not anybody in the WNBA, but this is going to go on and on forever. So what percent of this graph is shaded? That doesn't look like a whole lot. But this is greater than. So now my smallest number, my lower bounds, is going to be my 76, and my upper bounds is going to be 9999 to represent infinity. My mean is still 72, and my standard deviation is 2. When I plug that in, I'm going to go ahead and write this just as a percentage, about 2.28%. And that's taking whatever we came up with in our calculator, multiplying that figure by 100, or moving the decimal place 2 units over to the right. And we should be able to look at our graph and say a very small percentage of this graph, probably about 2.28%, has been shaded. What percent of WNBA players are between 67 inches and 75 inches tall? Well, let's kind of mark those. 67 inches would be about here, and 75 inches would be about there. And we're looking for in between those two guys. So this area right here, now we're not going to either extremes. We're not going to negative infinity or positive infinity. We're bounded between 67 and 75 inches. So when we write our lower bounds, that's a smaller number. The upper bounds is the larger number. And then the mean and standard deviation are the same. And we should get in our calculator should spit out something like this, which looks like our shaded area is the majority of this graph, right? There's very little parts of this graph that are unshaded. So we should expect this to be a relatively high number. This would be our proportion, 0.9269, blah, blah, blah. As a percentage, if I ask you that, multiply that number by 100 or move the decimal place and round it accordingly. So this would be a 92.7%. And this is representing about 92.7% of this graph is shaded, which makes sense. We can see that. All right, what about finding a data value given a proportion? So now I'm going to give you the shaded region, and you're going to tell me like how tall a WNBA player who is taller than this or shorter than this. So we're going to start by kind of visualizing this, and we have another calculator step that we're going to use. Make sure that you have these calculator steps, because I'm not going to be providing them to you. But we go back to second vars, but this time we're going to hit option 3, and this is when we are looking for data value and we're given the proportion. We're actually given this as a percent, so we need to convert this to a decimal first. We're going to create a rough sketch based on our given problem. So I don't know where this is going to be, but basically I'm going to be shading approximately what I think looks like 75% of this graph, which it's not going to be exact, but and I'm going to be shading the left side of a value because I'm looking at WNBA players who is taller than 75% of the data. In other words, whatever my number is, I'm going to say somewhere about there, maybe a little more than 74 inches, maybe a little less than 74 inches, I would say represents about 75% of this graph. I don't know what that value is, and that's what I'm trying to find out. But either way, what I do need to be aware of is where I'm shading at. I'm shading on the left, and this would represent how tall a WNBA player that is taller than 75% of all other WNBA players. So here, we're going to change our percent to decimal, and when we type in our second vars option 3, we're going to change the area to decimal instead of a percent. We have to do that or we'll get an error. And then we're going to type in our mean and our standard deviation, and you'll have this option on what tail to choose. If we're shading to the left of something, then we're going to choose left. On the right, we'll choose right, and we'll go down and hit paste. And we should see that about 73.3 inches would be somebody that's taller than about 75% of all WNBA players. I would encourage you guys to try this on your own. I'll kind of talk through it real quick. This one, we're going to do the right. This is saying how tall is a WNBA player who is shorter than about 75% of all WNBA players. So now I need 75% to be above some value. So I'm saying maybe somewhere between 68 and 71 inches. That this, once again, should represent about 75% of my graph being shaded. And this is purely just to get a visual on what do I select? Do I select right or left? And when we do this rough sketch, we can see that we have the right side that is shaded. So we need to change our percent to decimal. Everything else is going to be the same because I'm dealing with the same proportion, and I'm just selecting right tail because I'm shaded the right. And that would represent 70.7 inches would be a WNBA player who is shorter than about 75% of all other WNBA players. Let's look at another proportion problem. We can write this as a proportion or percent. Proportion is just the decimal before I multiply it by 100. But here I'm asking, what is the proportion or the area shaded of a price of Jordans that cost $247 if the mean price is $279 and the standard deviation is $16? I'm going to go ahead and fill out my normal distribution, putting my mean in the middle and going up 3 standard deviations above and below. And this is the area that I'm looking at. So what is the proportion of a pair of Jordans that cost $247 if the mean price is $279? So we would look at that 247. Anything below that, less than, is what I'm kind of looking for here. So my lower bound would be negative 9999. My upper bound would be 247. And my mean and standard deviation are as follows. When I type that in, I get something that looks like this. If I multiply that by 100, I get a percentage, 2.3% approximately if I rounded that. So what does this mean exactly in context of the problem? We can say that only about 2.3% of all Jordans sold are at or below the price of $247. In other words, that was a good deal. You're not going to probably find a better deal than that if you find a pair of Jordans that are $247 or less. Or you can think about it as 97.7% of all Jordans sold are at or above the price of $247. Okay, a couple more. We're going to look at these to predict the number of outcomes based on a proportion. So we're told that Landon runs the 400-meter dash. His finishing times are normally distributed with a mean of 60 seconds and a standard deviation of 1 second. If Landon were to run 38 practice trials of the 400-meter dash, how many of those trials would be faster than 58 seconds? We want to round to the nearest whole number. So we have a lot of numbers here. Some of these numbers are really kind of irrelevant. Like the 400-meter dash is the type of running that he's doing. I don't know what you call that, but it's a type of race that he's doing, 400 meters. So that doesn't have anything to do. It's just telling us some detail about what he's doing. When he times these, we're told that his finishing times are normally distributed with a mean of 60 seconds, which means on average he can run a 400-meter dash in 60 seconds, but he has a standard deviation of 1 second because some are going to be more, some are going to be less. So if Landon were to run 38 practice trials of the 400-meter dash, how many of those trials would be faster than 58 seconds? So we're going to start by setting this up, and that 38 practice trials is what we're going to do at the end. We're going to deal with that here in a second. So we're going to first figure out the proportion that he would run faster than 58 seconds, and then we're going to apply that to if he ran 38 practice trials. So if I set this up, 58 seconds would be about right here, and for him to run faster than that, that would mean he would want to run less than 58 seconds. So that would be this area right here, which should be a very small proportion of this problem. And so I'm going to do my lower, upper standard deviation, so on and so forth, just like we've already been doing. And when I do that, I get this in my calculator. So this is the proportion or probability, or however you want to think about it, that he would run faster than 58 seconds. So now we want to assume, okay, so let's suppose that he were to time 38 tries. So he's going to run the 400-meter dash 38 times. How many of those times would we expect to be faster than this? Well, this is our proportion right here. So if we take this number and we multiply it by his trials, right? Oops, I did it by the wrong thing. My number is going to be wrong. I multiplied it by 32 instead of 38. So whatever that is by 38, if I take that number and multiply it by 38, this number is going to be wrong on mine because I can see that I did 32. But it still should be, that number is not going to be exactly 1. So we would just round up. And so we would say if he ran 38 times, we would expect maybe one of those times he might get faster than 58 seconds. Is kind of what that means. At a local restaurant, the amount of time that a customer has to wait for their food is normally distributed with a mean of 30 minutes and a standard deviation of 5. If you visit that restaurant 24 times this year, what is the expected number of times you would expect to wait longer than 34 minutes? Round to the nearest whole number. So we're going to set this up like we did previously. Here's our restaurant. Our mean's in the middle at 30, standard deviation of 5 minutes above and below, label 3 above, 3 below. And then we're going to figure out where we need a shade. So we're looking at longer than 34 minutes. So I'm going to put a little mark kind of approximately where 34 minutes would be and shade to the right of that because that's going to represent the times longer than 34 minutes. Since I'm on the right, I'm going to find that proportion. And I get this in my calculator. And so now this proportion of the graph has been shaded. And if I'm visiting the restaurant 24 times this year, if this is my proportion of the graph, then I just multiply that by 24. And I get this. And what does that represent? That means that if I visit the restaurant 24 times this year, rounding this number, that would be about 5 of those times I would expect to wait longer than 34 minutes. All right, here we have IQ scores are normally distributed with a mean of 100 and a standard deviation of 15 out of a randomly selected 1,450 people. From the population, how many of them would we expect to have an IQ between 106 and 125? Let's set this up, find the proportion first. I don't know why I have a dot there. 106, 125 doesn't have to be exact. And then we're looking for this area in between. So that little area. So once we figure out that proportion of the graph, smallest, largest, and then mean and standard deviation, figure out what that proportion is, which is this. That's the proportion of the graph that's been shaded, about almost 30% of the graph. So now we're saying if 1,450 people were randomly selected, if 30% of this graph was shaded, then we're essentially needing 30% of 1,450 people. And I would just multiply by that, and I would get about 430, which means that if I collected IQ scores for 1,450 random people, I would expect about 430 of those 1,450 people I have sampled to have an IQ between 106 and 125. And that is all we have.